Good morning, everyone. I think we'll get started. Greetings from Pier 17 in San Francisco. I'm Mary Ellen Johnson, the head of exhibitions at Swissnex San Francisco, where we connect Switzerland to the west coast of the US in art, science, research, and innovation. Today, I'm delighted to introduce you to a panel of expert researchers from the University of Applied Science and Management of the Canton Vaud and the Lawrence Berkeley National Laboratory. They will share their research and discuss how we may face the complexity of future supply and demand of energy sources. We'll first hear our speakers present their research and then enter into a discussion and Q&A before we close our program. I encourage you, the audience, to add your questions throughout the program into the Q&A box you'll see at the bottom of your screen, and we'll address those after the presentations. Our first speaker today is Massimiliano Cabazzali, who has a PhD in theoretical physics from the University of Neuchâtel. He is Associate Professor of Energy and head of the Energy Competence Center at the University of Applied Sciences and Engineering and Management of the Canton Vaud. His research specializes in the new planning tools that manage the complexity of energy supply and demand dynamics. I'm handing it over to you, Massimiliano. Welcome. I think you're on mute.
Now you can hear me?
Yes, thank you.
Thanks, Mary Ellen. Thanks to all of you who joined for this very interesting session. I'm really looking forward to it. And I will present the case for networks convergence and explain a little bit why I believe that in the future, the energy networks will have to work together for a more sustainable future. So what is exactly meant by networks convergence? This has to be defined. This is a term which comes from the telecommunication system, where in fact the networks have already converged. And this is something which is presently arriving in the field of energy. The energy networks we are talking about are electricity networks, natural gas network, and heating and cooling networks. And convergence refers to the interaction on a given territory, although these networks might be operated and owned by different companies. Convergence has to be a voluntary and controlled interaction to answer specific needs. So it's something that you really want to have. It can apply to both distribution and transport networks, even if the contexts are completely different. And in fact, it may happen, and it is already happening, mainly on existing technologies, for example, cogeneration. And in fact, just to close the loop with telecommunications, the future energy smart grids will in fact interact with another network, which is the telecommunications network. There are new needs on these networks, and I will try to convey the message that convergence may be part of the answer. There are three current facts. All of the three energy networks we discussed about before have specific challenges. Their way of operating will change in the following years and decades. So we require new approaches. The electricity networks has its own challenges because of the penetration of intermittent sources, renewable, load variations, electric vehicles, bidirectionality. Natural gas network has a probable decrease of selling volumes due to increased energy efficiency in the building and industry sectors, and local carbon policies, which may represent an obstacle to natural gas. Heating and cooling networks have also a decrease of demand density, which is already foreseen, which may put in question their financial viability, but at least in many European countries have a strong political support. And also they have variable energy content in supply, in particular, if they are supplied by biomass. And so all the type of networks can in fact bring questions to one another if we look at the system as a system and not to look at the energy networks in silos. So we would like to take advantage of possible synergies among them. And in fact, natural gas network, be it supplied by fossil gas or in the future by renewable gas or even hydrogen, can play the role of flexible interface towards this network interoperability so that the networks work together. One of the keys to all of that is what is called power to gas or power to X, which in fact is what is turning electricity into a chemical energy carrier in order to take advantage of the physical properties of an energy carrier on the chemical form, for example, because of storage, and then possibly turn it into another chemical carrier, for example, methane, or convert it back to electricity by way of fuel cells. This is something which is being developed very fast at all scales, from very small scales of 10 kilowatts to 10 megawatts plants. It offers many possibilities, as you see here, to make the power infrastructure and the gas infrastructure talk to each other with very well-known, except maybe for methanation, very well-known and well-managed technologies. And the X in power to X could be heat, power, and gas, thereby increasing the flexibility of the system. The basic idea here is to be able to store, in fact, the excess production from intermittent sources. And in Europe, it is representing a real challenge. I'm putting here a few numbers. In 2013, what the excess production of Germany was of the order of 0.5 terawatt-hour. And in 2017, we had almost 200 hours of negative electricity spot prices, which in fact points to the fact that this electricity was not able to be used in the right way and was wasted in a certain sense. Power to gas could become, in fact, a key also to the coupling with heat networks, because of course, one of the buffers or one of the usage of this excess production could be heat. And maybe the future of our cities is, as you see here, with the three networks working together by way of technology interfaces, transforming the energy into each other. Of course, with conversion losses, but on the other hand, losing renewable energy production is not a solution either. So not to work in silos anymore, but to use the synergies among the networks. Renewable energy sources are clearly a challenge for the electricity network, in particular for the electricity distribution network, as you will see in the next presentation, because the production is intermittent at different timescales. It's partly decentralized. For example, think about PV in the residential sector. And the production, contrary to what was happening before, is often located far away from consumption centers. Think about the large offshore wind parks that in Europe we have in the North Sea, for example. So the future electricity network should include storage capacities. We will talk about them afterwards. Technologies that are able to absorb power when production peaks. For example, PV in the summertime. And here, power to gas is clearly an ideal solution. And at the same time, we should have generation capacities when you have consumption peaks. For example, when heat pumps during cold winter days work a lot and put, in fact, at risk the stability of the distribution network. And here, for example, decentralized cogeneration could provide answer. I believe that in all three cases, networks convergence can bring solutions, part of the solution, of course, for this. And this is an opportunity for natural gas and for future renewable gases. We are talking here about natural gas infrastructure, not about the nature of the content of this. In fact, networks convergence can bring answers to the electricity grid challenges, but to the challenges of natural gas itself. Because in fact, the sold volumes for it tend to stagnate or to decrease, for example, due to energy efficiency measures. It is irrational in front of political obstacles, for example, with respect to climate policies, with respect to fossil natural gas. It's an asset management optimization strategy, clearly, from a network viewpoint, where in fact you can develop new business models. It will allow the injection of renewable gases, in the future, even hydrogen. Germany just decided these days to go 20% hydrogen transport capacity inside the natural gas network. And it is clearly an answer to supply security, so to diversification. And it is clearly a transition towards a service-based business model. However, the framework conditions in many European countries, and I believe even in North America, are not existent or slightly existent or are just evolving. They are, in any case, suboptimal. And this is the understatement, the clear understatement, for example, with respect to the power pricing policies for power to gas plants. And the second question is, what will be the future role of hydrogen? Will we use it alone, or will we use it as blending with other renewable gases. So there are many uncertainties which tend to bring us to a chicken and egg problem, which is blocking the system. One example of one of the projects that we are still working on, it's networks in city, where in fact we are trying to optimize the natural gas network in an urban zone under constraints. And these constraints are very clear, very concrete. This is what is happening in our cities. Penetration of other energy conversion technologies, for example, heat pumps. There are building renovation policies, which can be very aggressive depending on the policies of a given city or a given territory. And the disappearance of one or more technologies because of these policies. Maybe a territory or a city could decide to forbid completely oil combustion boilers. So as a result of political decision. So we wanted to optimize the natural gas network under constraints which lead to a decrease in the demand, and take this decrease into demand and say, does the natural gas network survive, and how? And in fact, we discovered that it does not only survive, although it decreases in size, but it can also bring a very useful help for the electricity distribution system. So it's an optimization model which is based on demand covering. So we take the real heat demand of a complete Swiss canton of approximately 500,000 people. So we have the load profiles, and we will cover this demand with so-called acceptable technologies: district network, heat pumps, solar collectors, and cogeneration. And we consider a set of unacceptable technologies, for example, combustion of oil and wood. Wood, not because it's renewable, because Switzerland is a very dense country. So the combustion of wood in dense urban zones is sometimes forbidden, and most of the times not recommended. And then we consider the reduction of heat demand because of refurbishment of buildings, and a slow phase out of gas boilers and of oil boilers. And so we cover the demand and optimize the natural gas network with respect to this demand covering. And these are the results. And we see that, of course, the range and the intensity of these results depends on the hypothesis that we do, for example, on the prices, although we had a group of experts working on us on the parameters, especially on the economic parameters that we chose for the optimization. And we see that gas boilers tend to disappear on this territory, which was the canton of Geneva in southern Switzerland. And we see this increase of heat pumps and CHP. And what is interesting here is that we see that the heat pumps, in fact, by considering that they produce 30% of the energy that they generate as electricity, will in fact bring a very substantial help for the massive penetration of heat pumps on territories. So in fact, by replacing gas boilers by cogeneration, you foster the penetration of a partly renewable based solution like heat pumps by in fact sustaining the electricity distribution network. And we will continue working on that and control that all of that is real not only on an annual average basis, but also on a real-time electricity network simulation. So we'll further work on that. Here you see the evolution of the natural gas of this canton of 500,000 city. You can imagine some of the small states on the Atlantic coast of the US to have an idea of what this canton might represent in the US, like Rhode Island or Delaware. And you see that, in fact, the basic structure of the natural gas network, although the demand goes down, does not disappear. The mesh goes finer. There are many details which disappear. Of course, there are demand sites which disappear, but the basic backbone, and especially the redundancy, does not disappear. So the basic structure of the gas network does not disappear. Here you see that based on the real demand, we are able to, the optimizer is able to locate both the new CHP and the new heat pumps coming out of the optimization. And what is interesting is that not only you see that the CHP produce a large part of the new demand generated by the electricity-driven heat pumps, but in fact are very well distributed on the territory, so might really bring an answer to the lowest voltage level of the distribution system. And this is what we are going to test now with real electricity distribution systems, networks and simulation with my colleague Mokhtar Bozorg. And the last thing I wanted to say, and this will be my last but one slide, is that of course the total length of the gas network decreases, But this is a really interesting tool in the sense that if you have a gas network as an asset of a local utility of a city somewhere, you see that where you have to do the investments, where really even with these constraints which tend to say that this network might not be financially viable in the future, you have the possibility to really concentrate on the important parts of the network, and there where it can really bring a contribution to the transition. And the last result you see it here, by using standard attribution of CO2 per kilowatt hour, without going too much into the details, this is the expertise of my colleague Pierre-Yves Padet. Even by using pure natural gas, pure fossil natural gas for the substitution and this penetration of cogeneration, you see that in terms of CO2, the replacement and the massive penetration of cogeneration with heat pumps, so in a kind of a symbiosis, brings to very interesting CO2 reduction. And this is with purely fossil gas. Imagine what can happen if in the future there is even a slight share of biogas or renewable gas there, or hydrogen to use as cogeneration, for example, with fuel cells. So networks convergence is a solution set, which of course will come on top of many other solutions. And here the idea is to use renewable assets, that is the networks that already exist in our cities, and to use them together. And so it gives answer for this increased decentralized and intermittent generation for renewables, and it increases the supply security. It's of course also an investment optimization kind of approach, which is useful for the planning for both public owned or private owned utilities like we have in Europe or in North America. And so my basic message here is that energy networks should ideally be planned and then operated in synergy, whereas none of these things usually still arrive in our countries. But the question of economic viability and of framework conditions is not solved yet. And this is part of the future, because the technology has proven by this first optimization model, the technologies exist, and the approach shows us that using these assets together can bring solutions for the future challenges. Thank you for your attention.
Thank you so much, Massimiliano. Thank you. Just a reminder to our audience to put your questions into the Q&A, and we'll address those after the presentations during our discussion. So next I'd like to present our two presenters, Mauro Carpita and Mokhtar Bozarg, from the New Rennes Laboratory at the University of Applied Sciences in Engineering and Management of the Canton Vaud, where they test these control methods for smart grids, power electronics, and smart meter devices. They'll present how the transitions away from fossil fuels as the main carrier of energy transforms the way the grid functions. Mauro Carpita has a PhD in electrical engineering in power electronics from the University of Geneva. Since 2013, he's been the head of the Institute of Energy and Electrical Systems, and since 2015, the Deputy Dean of the Department of Industrial Automation. His research interests include power electronics and automatic control, particularly in high power converters, high voltage converters, and smart grid applications. Mokhtar Bozarg received his PhD from EPFL. Since 2019, he's been an associate professor in energy and power systems. His research interests include smart grids and active distribution networks, applications of mathematical modeling, optimization techniques, data analytics in power systems and power markets, integration of renewable energy sources, and energy storage systems into power systems. Thank you so much, both of you.
Thank you. Thank you, Marie-Ellen, for the kind presentation. And can you see my presentation on my screen? Or?
Yes. Yes, we can. Thank you.
Good. Okay. So this is a double presentation. In the first part, I will introduce our REIN laboratories. And in the second part, my colleague Mokhtar will show you some examples, some applicative example of the usage that we made of this lab. Okay, but first of all, I will try to connect to the kind presentation of Massimiliano, explaining why we developed this tool and talking about the energy transition. Okay, energy transition is creating a strong transformation in the actual, in existing electricity network, and because of several challenges. Those challenges are the increase of renewable electricity source, massive, the efficiency requirements that are strong, increasing, the introduction and the opening of electricity market, the requirements for increase the reliability and high quality of the voltage, of the supplied voltage by the DSO, an increase in the transport capacity asked to the network, and last but not least, the interconnection with other infrastructure, and not only other grids like Massimiliano presented, but also infrastructure that are mobility, telecommunication, etc. So the distribution network, medium voltage and low voltage, are expected to play an important role, a vital role in this context, even they are not being designed for this purpose. So something must be done. So distribution network, according to those challenges, will be characterized by at least two key points, key strong fact: a stronger penetration of distributed network generation and the presence of active consumers or prosumers. All those facts will increase the necessity of having observability and controllability of medium and low voltage distribution grids. Because nowadays, if the medium voltage is at least quite well controlled, low voltage is not controlled at all. So we need, distribution system operator needs tools. And those tools must allow to monitor and measure the status of the low voltage grid. And of course, in order to control, we need controllable resources. What I mean is power electronics inverters or power electronics for storage system, etc., that allows the distribution system operator to act on the production in order to adapt the status of the grid to the requirements. Those changes will result in the arrival and development of intelligent networks that are often called smart grids. One thing that must be clear: smart grids is not something that will switch from in one day, but there will be an evolution over the time. And in order to planning to develop those evolution at best, it is necessary to have platforms in order to be able to test the solution, the control solution that must accompany this development. So summarizing, we can define a smart grid like an electrical system for which we have information. We have a flow of the information in two-way and protected against cyber attacks. And the computational intelligence is integrated everything in the production, transmission, substation, distribution, and also in the consumption. And the purpose is to achieve a very good system. I mean, clean, safe, secure, reliable, etc., etc., etc. So this is the context. RHEIG Laboratory. RHEIG is RHEIG stands for Réseau Intelligent, which is the French translation for smart grids. We had a lot of fantasy in order to choose our names. Is a platform and that allows the emulation of a great number of different network topologies in a real time and on a real scale. This will allow to test the smart grid control algorithms, as well as power electronics and other grid-related devices under control condition and under generation constraints. Those are the characteristics. As you can see, the voltage level, nominal voltage level is 230 or 400, while on delta. The topology is 8 lines that are arranged in a controllable matrix. I will give some details later. And a 9th line that is free. The line are emulated with discrete inductors. Resistors have been already added and capacitor can be added. Nominal power is 100 kVA. Nominal current is 135 amps. And there are several equipments, loads, and several production device, real and emulated. I will speak about the control later. And the research is, and the utilization, sorry, is for research and educational application. You can see on the figures on the right some glimpse of the laboratory. Okay, flexible structure. What does it mean? It can be reconfigured. We can choose our topology and create it in a very fast and repetitive way. We can choose freely the connection points of the different sources and charges. And this is as far as the main area is concerned. Monitoring, we have a high frequency sampling, 50 kilohertz. And we have data acquisition, which is based on GPS synchronization. And we have 2 sets of control. One is based on national instruments, hardware and software. And the second one is based on grid-eye system from DEFSYS SI. DEFSYS is a startup, is a spin-off of our institute that started his activities in this domain in 5 years ago about. Okay, you can see in the figure summarizes some of the main characteristics of the 2 systems. So I will skip to show you what we can do. In the second, sorry, I will take this pointer. In this photo, in this design, you can see different kind of grid that we can achieve, partially meshed district, a low voltage district, for example, and or a fully meshed grid. And this can be achieved, those different configuration can be designed with a SCADA interface and can be deployed in the matrix switchboard that create the structure of the lab. I will terminate my presentation just to spend a few words in a peculiarity of this installation. We have developed also a smart home whose purpose is mainly educational, but not only, because we can also make tests of industrial devices like measurement devices, let me say smart meters, for example. We can make performances tests on appliances, household appliances, and we can also study or making tests about system service strategy. What are the characteristics of the smart home? We have a photovoltaic installation with panel on our solar carport. This is the size of about 20 cars that can be located there. We have an AC battery for energy storage. AC battery means battery plus inverter. We have a water heater that can be connected to the photovoltaic installation. We have a refrigerator freezer. We also have some other small equipment that I'm not describing today. So I finished my introduction, and I give the words to my colleague Mokhtar Bozorg that you will speak some application project that we made in this lab.
Okay, thank you, Mauro. Could you please move to the next slide?
Yeah, okay.
Okay, great. In the next couple of slides, I'm going to present few projects. It's just presentation of main idea of the project that applies actually the hardware infrastructure in the brain laboratory, but also simulation of and emulation of distribution grids in general. So the first one, SMILE-FI, is a project supported by Swiss Federal Office of Energy. The key idea is that we have resources that are installed at the low voltage or medium voltage distribution grid, mostly, let's say, low voltage. And we want to take advantage of flexibilities of these resources, either control of photovoltaic inverters, as Mauro said, or local battery storage. But to provide these flexibilities at the point of connection to the higher voltage grid, the problem is that most of the time with low voltage distribution grids, the parameters and configuration of the network is not available, or it's available, but the information is not up to date. So the idea is to develop a control algorithm based on sensitivity coefficients that makes a link between measurements of voltage and power at local level and power or flexibilities generated at the medium voltage level. So these kind of algorithms, they can use observabilities of network through installation of measurement devices. So through the history of data from these measurement devices, we could compute these sensitivity coefficients, and thanks to these sensitivity coefficients, we could optimize the flow of power, or active or reactive power, to our higher level of voltage. And this kind of algorithm has been tested in our RAN laboratory. Next slide, Mauro, please. In the next Thank you. In the next project, we take one step further from real-time control of the network. We said, if you have a history of data from these measurement devices, can we use this data to plan the evolution of the network? So one of the questions is that, for instance, at every node of the distribution network, what is the maximum capacity of residential photovoltaic installation that we could install and our network could host without violating grid operation limits like over voltage, under voltage, local congestion, and so on. And again, we use in this project the sensitivity coefficients to optimize the planning process without even knowing the exact parameters of the lines and cables. The same strategy on planning for overproduction can also be done for installation of new charging station for electrical vehicle and increasing the power consumptions. Next slide, Mauro, please. Well, here in the Grid Data Synergy project, we've recently worked with the distribution system operator of City of Geneva. We use these measurement devices on a grid side, let's say, installations, in combination with data that are available from households. So we have two sources of data. By we, I mean the distribution system operator. So they have their own installation of grid measurement devices that measure voltage, power, current, and so on. And they have household data, the active reactive power consumption coming from smart meters. And the idea is how to use these two sources of data to run state estimation, improve the observability of the network. And the main challenge is in this kind of application is that smart meter data are not available in real time due to legal and privacy issues. So they are available in like 24 hours delay. And on the contrary, grid measurement data are available in real time. So how to mix these two to run real-time intraday forecast based on these two sources of data. And the next slide, Mauro, please. The last next one. Thank you. And the last project that I'm going to introduce is Grid Data Digger, in which we are preparing an automated assistant tool for distribution system operator in case of having access to thousands of data from thousands of measurement devices. So how to ingest this data and how to analyze this massive amount of information coming from measurement devices. So we need to run it on a big data platform to do the ingestion of data, pre-analysis of these data, and provide both analysis and control for the distribution grid. The next slide, please, Mauro. And just to conclude, I have some results of this, let's say, this assistant tool for distribution system operator. So in left, we can see a small city of La Chapelle in Switzerland, where we have the medium voltage transformer, a number of electrical cabinets. And the question is that with the history of data, for instance, of 1 year, what are the most representative days that we can use in terms of profile of power to do the planning and simulation of the network? And these are in blue, orange, and green are three categories of the most representative days of this network, using a clustering approach based on historical data that we obtain. I am done with my presentation, and I pass, I think, to Pierre-Yves for the next.
Yes, thank you so much. Thank you both for your presentations. Next, I'd like to introduce Pierre-Yves Petit from the Thermal Engineering Institute at the University of Applied Sciences and Engineering and Management of the Canton Vaud, where he's the scientific collaborator specializing in life cycle assessment for energy production and consumption in the building sector, encompassing the questions of variability and uncertainty of energy. He received his PhD in energy and processes from Mainz Paris Tech in 2013. So thank you.
Okay. Thank you for this introduction. So I will present you today the results of one of the projects we had here at University of Applied Science regarding the dynamic environmental impacts of the electricity consumed in the building. So just before digging into the real subject, there's a few words of context and scope regarding the Swiss electricity. So in Switzerland, there is a large amount of production of electricity, mostly relying on hydro and nuclear energy. These two energies are supposed to have a low carbon footprint, but the problem is that Switzerland is not self-sufficient, and even more during the last years. So there is a large share of imports from the European network, mostly from Germany and France, as you can see on the graph there. And this will have an influence on the environmental impact on the Swiss consumed electricity. And however, currently the impact of the electricity, the calculations are mostly relying on annual statistics. So there might be an underestimation of the impact, especially when you have seasonal demand, such as for space heat, which occur only in winter. So the question of the research question for this project was first to see how the hourly supply mix of the in Switzerland can affect the environmental impacts, and what is the discrepancy with the current calculation approach that is on annual basis. Then we can ask ourselves what is and how we could develop demand-side management approach in order to adapt the building energy demand as a function of the grid impacts. And finally, what would be the impact reduction potential for such kind of approach. So this was the goal of the project. To do so, we developed a methodological framework from the data of production to the environmental impacts. So first, we collected the data from the production means in all European countries, and we focused mostly then on Switzerland and its neighboring countries. So we got for 2 years, for instance, the exact production of each type of energy sources, coal, gas, and whatever, from these countries, as well as all the exchanges, import and export between the countries. Then, based on this data, we were able to develop and to obtain what is the supply mix of the electricity in Switzerland from hours to hours. And we converted this, production mix with life cycle inventory database, namely EcoInvent, in order to get the hourly environmental impact profile of the Swiss consumed electricity. And finally, on the third step, we collected data on buildings regarding the electricity consumption for different type of needs, such as space heating, domestic hot water, or electric appliances. And we also consider when there is decentralized production. And we then make the calculation for the environmental impacts of the building electricity demand and compare to the annual calculations. So which type of data did we obtain? So then collecting the data from the European Network Transmission System Operator and merging them with some information from the Swiss Federal Office of Energy, we were able to obtain such kind of results, which shows what are the production means that are switched on at each time of the years in Switzerland, and then what are the imports and exports from Switzerland. And within the imports and export of the country, the neighboring countries, we knew exactly what were the production means that were operating at each time. So as you can see, for instance, Switzerland, as I said, Switzerland imports a lot of electricity from the neighboring country, and especially in winter, they import electricity from Germany. The national production is mostly relying, as I said, on hydro and nuclear, and we export a lot of electricity to Italy, mostly all along the year. There's no high peaks, let's say. So based on this data, we were able then to calculate the environmental profile of the Swiss electricity. And here I focus only on the carbon footprint profile. So you have the results there for 2 years, 2017, 2018. And you have the breakdown of contribution per countries and per production mean. Let's say big categories of production means. It's presented here on daily basis for the sake of clarity. What we observe here is that we have large variability of the impacts. And we see that the German contribution, which represents about 20 to 30% of the supply mix, then contribute in terms of environmental impact to 63% of the impacts on average. So it's the main contributor, mostly because the electricity produced in Germany in winter especially rely on coal and gas. So it increases a lot the impact of the electricity consumed in Switzerland. So we have peaks in winter because more import, less availability of production mean in Switzerland because of snow, less hydro, and etc. And we also have valley in summer because we have less demand and more production, national production. So we will have a large influence on the impacts of the building electricity demand, especially when they are operated with heat pump or direct electric heater. So there is a large space for environmental optimization. So how it looks like at the building level. So as I said, we collected data on 6 different case studies regarding the electricity consumption from hour to hours, and then look at the needs for space heating, domestic hot water, and other electrical appliances, as well as the photovoltaic production. And we tested different scenarios based on this data, and we obtained the hourly carbon footprint of the building electricity demand. And you can see that there is high peaks in winter, again, because you have more demand because of space heating, but you also have more impact of the consumed electricity and less availability of photovoltaic electricity. Then when we try to see what is the influence of the time resolution when we make the calculation for the environmental impacts, so we compare the results considering monthly, daily, and hourly calculation compared to the annual calculation that is the current practice. And we can see that the higher the time resolution here, the higher the impacts are. And this is especially true for the electricity related to space heat, because this needs occur in winter, so you have much higher impacts than if you consider annual calculation. So the current calculation underestimates the impacts of the building electricity demand. So it's really important to take this into consideration for the calculation of the environmental impacts at the national level. We also observe a bigger sensitivity for the single family houses, probably because the share of the space heating is more important. And we'll see also that the carbon footprint impact is more sensitive to the variability of the time step choice compared to other environmental indicators, such as non-renewable primary energy. And finally, the domestic hot water and domestic appliances are not really affected by the time step choice because their electricity needs related is more or less constant over the year. So it's really related to seasonal demand. So as conclusion, we can see that the environmental impact of the electricity is not constant over the year. And there is, of course, a large variability related to demand and supply availability. So there is a need to take this into consideration. And the Swiss impacts are largely related to imports. So we need really to take this into consideration for the energy policies development. At the building level, the space heat demand supplied by heat pumps and electricity, direct electrical heaters, have much more higher impact compared to annual basis calculations. So we need to take this into consideration again. And there is a large space for DSM, so demand side management solution, including also active solutions such as storage or whatever, in order to mitigate the environmental footprint of the energy demand. And finally, as future research that could be considered, I think we could probably use such kind of hourly environmental impact of the electricity for other domains, such as electric mobility. So to develop environmental profile calculation for the charging of the electric vehicles and their interaction with buildings, for instance. And in a broader scope, we could also consider such kind of information for data center operation in order to try to minimize their environmental footprint as a function of the impacts we have on the grid at a certain time. So, but there is a need to develop forecasting tools that predict the environmental impacts few hours in advance. So I thank you for your attention, and you have more details if you want on some publication for which here I put one links on the presentation.
Thank you so much for that presentation, Pierre-Yves. Finally, I'd like to introduce our last speaker for the morning and our moderator, Alan Meyer. Alan is an adjunct professor in the Department of Environmental Science and Policy at the University of California, Davis, and a senior scientist at the Lawrence Berkeley National Laboratory, where he leads the Electronics, Lighting, and Networks group. He earned a PhD in Energy and Resources from UC Berkeley. Alan's research focuses on understanding how energy is transformed into useful services and the opportunities to use energy more efficiently with the assistance of technical and behavioral solutions. Thank you, Alan.
Thank you very much. You can see my screen, I hope. So let me get back to the title just for a moment. It seems that it's leading through it faster than I wish to. So I'm going to talk about how we are using existing sensors in the cable television network to track the voltage and power outages in real time. I would also like to acknowledge my colleague, Sunhee Baik, who has been working with me on this project. And in effect, this project illustrates many of the concepts that you saw in Switzerland. We have exactly the same problems in the United States. And I'll put it a little bit more bluntly. I think that what you see right now is three very important transformations occurring in the distribution part of the grid, which I would call the edge of the grid. That is the electrification from electric vehicles and fuel switching. We know about the local generation that is occurring now, thanks principally to photovoltaic, but also some wind, and of course the influence of batteries. And finally, we're going to have the effect or the impacts of extreme weather, and those show themselves at the distribution level. And so as a result of these, we know that we need to have better visibility into the grid conditions at the edge of the grid. And all of the previous speakers said the same thing, although slightly different, in slightly different words and for a different country. So we actually took a project or an existing network to and harnessed its sensors. It turns out that the television cable network has nodes delivering the cable TV signal to approximately 90% of the US households. And these nodes, there are about 75,000 of them in the United States, draw power from the grid locally in the region of every 250 homes. And so there is a power supply that powers that little node. And that node, it turns out that power supply is very sensitive to, to the grid, to the electricity supply conditions. And so the the service provider, the cable television service provider, is constantly, continuously monitoring the health of that power supply. So it, in fact, has a little sensor on the power supply observing in real time what is the voltage, incoming voltage. So in effect, it is watching the voltage in every neighborhood of the United States in real time. And the electric utility companies have to this date not used this information. And it is not simple, however, because the topologies for those two networks are not the same, but it still gives an opportunity for another kind of sensor to occur. So I'm describing a little project in that area. And in fact, this is the region that we studied here in Northern California. It's a small utility, and there are only 48,000 residential customers in there, but there are 105 of these television cable TV nodes there, and they are continuously, every 5 minutes, reporting the voltage that they see. So it has created a very dense network of sensors at the voltage, at the distribution level. And this is the kind of data that we would see from a typical sensor. We would know the sensor ID, we'd get a timestamp, it would tell us what is the voltage that it sees at that instant and the status of the inverter. And there, as you can see down at the bottom, there are three kinds of statuses that we're concerned about. One, that it's getting power from the grid, one that it has it's relying on a battery that is connected to the node, or it's not reporting. But as you can see in this example, there's at one point is 120 volts, another is 116 volts. And so in this way, you can sense at a very granular level when there is a power outage. And here you can see that we observed a power outage at these sensors. And this is what our data would look like during that period. And we can compare that to then what the utility is actually seeing. And we, in a sense, have better knowledge of what's going on in the neighborhoods with respect to power outages than many of the utilities. And we can also observe voltage anomalies. In this case, there was an external event of a balloon interfering with some of the higher voltage lines. And this is how that anomaly appeared in the service area according to our sensors. So based on that, we can see that, like several of the other speakers described, and in fact, perhaps in different ways, we see this convergence of the power network and the communications network. And it's especially the case at the edge in the distribution area. And in it, we see that the communication, this network that we have captured has provided new kinds of sensing capabilities, because we can see for the first time any voltage anomalies created by photovoltaics, electric vehicles, and maybe batteries being installed very much at the edge. And as other speakers alluded to, we also need to worry about the security and resilience of the system. So as a result, this system is completely independent of the utility communication system. And that is the best way to assure the security and resilience. And finally, this system already exists. And so it's very cheap. And so it avoids investing unnecessary money in a new sensor network. So with that very short introduction, I'm going to stop and hope that we can dedicate the rest of the time to questions.
Great. I welcome everyone back to the screen, and we can have discussion and address some of those questions in the Q&A. And just a reminder to the audience again, you're welcome to insert your questions for any of the presentations or topics.
Maybe, Mary Ellen, I'd like to start with just a summary sentence or two, if that's okay.
Okay, great.
I think that what you saw in all of these presentations was that there was the speakers describe the networks and the different, and there are different perspectives on it. And they weren't all the same, and they weren't totally agreeing with each other, but you could see the necessity for measurement, control, and the concern for the time scales that we saw from literally microseconds to years or decades in the kinds of analysis. And that's what I think makes this area of the grid especially exciting right now, that we need to worry about that entire spectrum of activities in a way that might not have been necessary 20 years ago. So with that, I'm quite happy to open it up to questions.
All right, well, we have a number of questions that were in the Q&A. Actually, the first question we received was in response to Massimiliano's presentation. So perhaps we should start there. Why do you propose gas as the energy source capable of enabling the interoperability between the three networks: electric, heating, cooling, natural gas? Do we have Massimiliano here?
Yes, here. I have to unmute myself, sorry.
Okay.
In fact, I'm not proposing natural gas. I'm proposing the natural gas infrastructure. So the network itself, it might be fossil natural gas like it is right now, and in the future, hopefully as fast as possible, renewable gases or hydrogen. In fact, chemical energy is more easily storable than electrical energy, and this is the main argument. In fact, the intermittency of production of the new renewable sources like PV or wind can be compensated, in fact, in a certain sense, by the storage capacity that chemical energy carriers bring to the system. So we have an existing asset, which is the natural gas transporting and distribution infrastructure, which we can use as a buffer. Of course, you have conversion losses, but again, instead of overproducing or maybe relying on other fossil sources to compensate peak consumption, it would be better to use the existing asset from that point of view. So it's really about the infrastructure that we want to use together in synergy, and not about a single energy carrier. I hope this answers your question.
Thank you. And we also have a number of questions. I believe the first ones were directed to Mauro and Mokhtar. The first question is, does the interconnection model of the commercial internet become a model for the convergence in this energy space? And has that process been modeled so that a proof of concept is recognized?
Tu veux répondre, Mokhtar?
Yeah. So not as far as we are aware of. So from our side, actually, we work on for the internet side, we worked on ensuring the cybersecurity for our network. But the point is that until now we have a vision of taking internet network as a service for power network, rather than in the, I mean, it's emerging to have the vision in the other way around. For instance, the usage of energy management of data centers for optimizing their power consumption, or even provision of flexibilities by shifting the power consumption is a way of thinking of convergence between these kind of networks. But I'm not sure if this could answer the question of the attendee, but this is actually just my viewpoint on the internet networks and its convergence to the power networks.
Great, thank you. There's also a question directly for you, Mauro. Is Is GridEye open source? Can GridEye be used as the common interface?
No, GridEye is by no means an open system. GridEye is developed by a private company that is called Depsys, and typically sold to DSO, distribution system operators. GridEye is made of both hardware measurement system and software tools that makes all the information available to the distribution system operators. And Mokhtar shows some improvement that we developed for them and with them in order to make this mess of this big quantity of data in order to make them available, the standardized information.
Great, thank you.
You're welcome.
We have another question. Is the first step to monitor this convergence the development of measurement tool that is accessible to individual households?
Yes, of course, I agree.
Yeah, okay. And then there's also a question for you, Alan. Is your idea of an existing edge sensor network compatible with the natural gas infrastructure as well?
Not really. What we are using in this case is are the nodes that are already owned by the cable TV network, and they are only measuring the electricity use of the grid. And therefore, we don't have to worry about personal information, first of all, but there's no measurement of gas. And so I don't know how that would be used directly. However, even though I say no so confidently, it's possible that some gas appliances could become connected to the internet and then provide similar kind of information to some sort of service provider. The problem then arises that we have to worry about personal personal information and privacy. So the answer is not right now, but maybe in the near future we could imagine some internet connected gas appliances. But I'm having trouble imagining what they are.
May I add something?
Please.
Regarding cogeneration, when Germany decided after the Fukushima accident to get out of nuclear pretty quickly, just Germany will get out of nuclear completely in 2022, and these are Germans, they will do it. One of the ideas which came out, in fact, from Volkswagen, so the car manufacturer, was to create what they called a swarm of generation based on micro cogeneration. So to have standard cogeneration units, of course, with Volkswagen engines fed with the natural gas, and to have millions of them dispersed on the territory, and with the idea of replacing gigawatts of generation that will disappear because of the nuclear phase out of Germany. And in fact, this cogeneration, this project has not been put in place for various reasons. But in that case, it would have been highly connected millions of micro cogenerations, which would have worked together based on the electricity demand in a very real-time kind of fashion, and at the same time providing heat to the houses where they were. And the business model which was behind, which was based on a fee for the heat demand, but on a premium, in fact, for the electricity which was produced in order to balance the overall German electricity system, was very interesting. And I hope that some of the obstacles that this idea had can be overcome, at least in the countries which will have, like Switzerland as well, to face a nuclear phase out, so a substantial decrease in electricity generation. This is the only example I'm aware of.
I think that's an excellent example, and I think I'm going to backtrack rapidly in my confident no and say, yes, there are some examples like you described, and also there are situations where we have natural gas backup generators in homes, increasingly in the United States. And while I don't believe those are connected in any network way to the and providing information to the internet, they could relatively easily be connected and in that way provide additional information. But like I said, the beauty of this cable television network is we don't need to worry about privacy or anything like that, and the infrastructure already exists.
Mary-Ellen, may I can add something to my
Please.
previous answer that was very, very laconic. So,
Yeah.
Maybe it's useful for the attendees, not specialist attendees, that to understand what is and what was the situation about the low voltage grid when we started those kind of activities 5 years ago, and we made interview with some distribution system operator in Switzerland. Just for information, there are more than 700 distribution system operators, so it's very, very vast group of operators. And they said, we are not interested in those kind of things because everything is planified. When we have new customer that they ask to be related to the grid, we make some simulation and we evaluate if we can give them the current energy, and that's all. And we asked, what about current congestion, and what about if they're producing energy, like it's happening now? So clearly, and sorry, that was the key point of my answer. And at that time, we realized that there were nothing at all, neither measurements in the low voltage. The only thing that was measured was the voltage of the output of the medium voltage, low voltage transformer. That's all, and that cannot guarantee nothing because, of course, this can become a mess if, especially if you have a lot of generation, distributed generation that can make also create an inversion of the flow of the energy remounting bar toward the medium voltage grids. So I repeat, to answer to the question, developing a measurement system is the backbone, is the key that allows to control the system. And this is always true for every kind of control application.
Thank you. I think, Alan, is there something you want to say? Or are you?
All I can do is agree and say we were shocked that the cable television industry and the service providers had better information and visibility into the real-time status of the distribution network in the United States than any electric utility.
Yes, and in Europe is exactly the same, but we don't have this kind of grid, of television grid. So, no, we have it, but not so diffused.
Curiously, there are companies like the bank machines, the ATMs, we call them, that the cash machines. They are another kind of network that can provide information and insight, at least about outages, maybe not about voltages.
Yeah. May I ask you a question, Alan?
Please.
What about the privacy matter in using the data from a cable company? And is there any delay between the availability of the data and the actual measurements?
All of the data are collected for a neighborhood, and it is collected on a meter on a sensor that is owned by the cable provider, by the cable television provider. And so there is no privacy issue, and the measurements are made every 5 minutes, and they are returned to the cable provider every 5 minutes. So they have near real-time visibility.
Okay, so you have a delay of 5 minutes.
Yeah, and that could be improved over time.
Okay, thank you.
May I add a remark here?
Please.
Maybe the application in Switzerland in few cases could also be interesting because some of cable TV providers are the same as electricity providers, like Service Industriel of Lausanne, so the industrial service Lausanne who provide electricity, gas, and also fiber optic and TV and cable TV.
But they measure the status of the grid.
Good question. I mean, we need to discuss with them.
Well, this is a good and interesting approach that we have to fulfill, to investigate at least.
This is an area for collaboration.
Yes, of course.
So we just have a few more minutes. There's one more question that maybe we could just briefly address, and then we'll have last thoughts. The question is related to Pierre-Yves' presentation. Being able to predict the carbon impact of electricity at a given time could lead to dynamic related to its carbon impact in order to consume less when it's coming from the German fossil. Is such a pricing model in discussion? Do I need to repeat that differently, or did you get that?
Yeah, I got the point.
Okay.
Thank you for the question. There is no real pricing model in discussion so far. What we must admit so far is that we made the calculation and the physical flows. I should have maybe mentioned it. And it's just like to then get the information first. And I think it's quite relevant with the discussion we had so far, which was first to know the information and to get the data, know how to use them and how to make them. There's a lot of different opportunities that needs now to be answered. But first we needed to get the information on how it looked like. So far it could be interesting, but it has not been considered.
Okay, thank you. I think now maybe we'll turn to our last thoughts. Unfortunately, we're almost out of time. It goes by quickly. Maybe I'll start with you, Massimiliano. Do you have a last thought or something you want to share with the audience?
Well, I think we need to move more and more to a world where we need energy services. It can be heat, it can be electricity for various things. Electricity, which can be used also to decrease our energy demand. I'm convinced we can consume a little bit more electricity if it means that it is used to decrease our energy demand. So what is important is to decrease the energy demand. That is the important indicator. And in a world of energy services, you're not paying for one or the other energy vector. You choose the energy technology, which provides it with the lowest possible environmental impact at the time where you need it. And this is the world where I hope we can move. And for networks convergence, the technologies exist. Although power to gas is not completely developed, it is based on an existing technology, which is electrolyzers. It's just a matter of using them at the right time. Cogeneration already exists. In the US, 11%, if I'm not wrong, of your electricity generation is done by CHP, mainly on industrial sites. So it's existing technologies. Is now a matter of framework, of political decisions, and of a change of mind with respect to that. And again, it was about gas transport infrastructure and not the natural gas per se. Get out of the energy vectors. Think about the energy service that you need and the lowest possible environmental impact.
Thank you. So we have 1 minute left. So Mauro, quickly, do you have a thought?
He's muted.
Oh, you're on mute. You're on mute.
Okay, so there was a question from the audience concerning the availability of the REIN laboratories for collaboration, and of course we are interested. So please do not hesitate in writing us and see what can be done from remote. We are available. So
Great, thank you. Mokhtar?
So just in 2 words, we need to improve controllability and observability of low and medium voltage distribution grids to realize energy transition and integration of renewable energy sources.
Pierre-Yves?
Yeah, just a word. Don't forget the environmental impacts, because it's supposed to be the basic idea why we are doing everything like this.
Great. Alan?
Thank you, everybody, for attending. I have no further words. Everybody said it for me.
Great. Well, thank you, everybody. Thank you to our researchers, our speakers. Thank you to our audience. Thank you so much for joining us today. It was a great way to spend our morning here and evening in Switzerland, I hope. Thank you all.
But it's not morning.
Goodbye.
Thank
Bye.
you.
Bye. Thank you.